Hello! Today we are gonna look at how to solve the finite vibration string. Okay, the vibration string, the equation is given by this hyperbolic type, such as the second derivative in time equals to c squared uxx. Okay, because we are looking at the finite interval, so my x is considered from 0 to L and t greater than 0. So we can have the boundary condition given at x is 0 equals to 0, and when x is L, which is also equals to 0, and we have the initial condition given by ux0 equals to f of x and partial u over partial t at 0 equals to gx. Okay, so what this boundary condition tells us? So we're considering vibration string. So if the string is fixed at both ends, this is what it means. Okay, this boundary condition here means string is fixed at both ends. Okay. On the other hand, if the string is initially displaced into a position u equals to fx and released at rest from that solution, okay, from that position, then this is what the boundary condition here have. So this initial condition means the string is initially displaced into a position u equals to fx as time 0. Okay. Now this initial condition also means that the initial shape of the string is fx. And then so here we have gx. We have the equation, the other equation equals to gx. And let me explain furthermore about this equation when time 0, where you get fx here. So there are two things we can say that, because this is the initial string displacement. So I just write it again, initial string displacement. Now, because we have a derivative here, that means that this is the initial string velocity. Okay, now, what else can I say? If, let's say, you're given this derivative equals to 0, that means the velocity everywhere of the string is 0, okay? Okay, so in this case, we don't have a 0 velocity. We have the initial string velocity given by gx. Okay, so this type of problem here. This is a type of wave equation. Okay, it's a type of wave equation which is from hyperbolic partial differential equation. Now, today we're going to look at how to solve, okay, how to solve this equation. Okay, so I've mentioned that the boundary condition, it means the string is fixed at both ends, and while the initial condition gives the initial shape of the string. So how we want to solve this? We're going to use a technique called separable variable, or we call it maybe the better notation will be separation of variables. Okay, so if you remember in your ordinary differential equation, you separate the variable to solve it, right? So the same approach we're going to use here. Okay, so start with by letting my u. So I want to find the solution u x t. See, I'm given as u, which is you have second derivative in terms of time and x. Okay, the position x here. So I want to find the solution u x t. So let u x t equals to my big X and big T. Okay, so this x is a function of x alone and t is the function of t alone. Okay, now because we have second derivative in terms of time and second derivative in terms of x, so we want to differentiate twice for t and twice for x. So differentiating once for x, where x here remain as a constant to become derivative. Now differentiating second time, that will give me second derivative in time. Okay, now similarly, if I'm taking the derivative respect to x, so I have x prime t, and then second derivative in terms of x, x double prime x, t, sorry. So there's no prime here because t remains as a constant. Okay, t is a constant now, so only derivative respect to x. So, okay, and this is like this. Okay, so we have an equation where now I can write this in terms of the given wave equation such that utt equals to c squared uxx. So utt is my xt double prime. I'm going to just ignore this x term. We know it's x. X is a function with x alone and t is a function in t alone. Now this one uxx given xx double prime t. Okay, since I've mentioned this is you can use separation of variables, so I can separate the variable here. So that will give me okay, this is what is called we have done a separable variable here. Now if you watch my previous video on solving heat equation, we have used exactly similar approach. Okay, so the similar approach is for this equation to be whole, we need to introduce separation constant. Okay, which is I'm calling it as lambda. Okay, now equating both sides will give me a second order ODE. Okay, this is my second order ODE here. Okay, so I need to solve for this equation. Now, to do this, we have to find the solution by using integrating it. Okay, so let's consider, because my lambda here is a separation constant, we need to consider three cases for my separation constant lambda, where case 1 is when lambda equals to 0, case 2 when lambda is greater than 0, and case 3 when lambda less than 0. Okay, so what we can do here, let's consider case by case. Okay, so before we even do that, okay, now let's consider the case 1 first. So I'm just going to focus on if you look at the initial condition given, the first condition given, okay, we can say that if uxt is to satisfy the first boundary condition, okay, first boundary condition, which is u0t equals to 0, then what we will have u0t when x is 0, right? That will give me 0. Okay, for all time. Okay, that means that since t is changing with, this function t is changing with time or t, the only possibility that this can be true if x0 equals to 0. Okay, so this is going to be our new or updated boundary condition. Now the second condition, similarly, we have ULT equals to 0. That means we will have, when x is L, I will have like this equation. Okay, and similar to the concept that we applied earlier, that will gives me x of L equals to 0. This is my second boundary condition that I want to look at. So by saying that, so let's just consider the x, big X term here that we have obtained just now. Okay, we're going to consider 3 cases. So case 1 is when lambda equals to 0. So I have the second derivative equals to 0. Lambda is 0 right now. Okay, this is not that difficult. We just gotta integrate it twice, right? So integrating twice, that will give me ax plus b. Okay, now applying the updated boundary condition such that when x is 0, I will have b equals to 0. Okay, now by the second boundary condition, now I have my solution here because b is 0, ax. Now with my second boundary condition, which is when x is L, I have AL equals to 0. Therefore, we know that A equals to 0. This gives me trivial solution. Okay, so we cannot consider the case 1 when lambda equals to 0. Now let's look at case 2 when lambda greater than 0. So to do that, we need to consider a lambda value that is greater than 0. So I'm going to let it equals to kappa squared. Okay, this is a positive. It will always be greater than 0. Okay, now by equating this, we need to find the second derivative. Okay, so I'll have x double prime minus kappa squared x equals to 0. Okay, the solution for this should give me two different roots. So I can write it as c exponent kappa x plus d exponent negative kappa x. Okay, so we have two different roots here. Now, it's easy to understand for this finite interval. We can write this in terms of cosh and hyperbolic cosh and hyperbolic sin. So recall, maybe I'll just write a note here, your hyperbolic definition, another use of hyperbolic cosh x, I can write it at exponent x plus exponent negative x over 2. And also for my hyperbolic sine function, I can write it as exponent x minus exponent x over 2. Okay, and then what we're going to do here, we want to change it, this term here, this equation here, in terms of hyperbolic cosh and sin. So we let c equals to a plus b over 2 and D equals to A minus B over 2. Okay, now look at this equation again. How I'm going to change it? Okay, so I have A plus B over 2 exponent kappa x plus A minus B over 2 exponent negative kappa x. So expanding this term here, okay, I have A exponent kappa x plus B exponent kappa x over 2 plus A exponent negative kappa x and minus B. Okay, you can see the pattern there. Collect the same constant equate, taking the A first. So I have half A exponent kappa x plus A exponent negative kappa x. Okay, and then this one will be B. I got a half here, B exponent kappa x minus with B exponent negative kappa x. So you can see that the similarity between this hyperbolic cos and hyperbolic sine term here, okay? So therefore, I can write this term as, so we know that exponent kappa x plus exponent negative kappa x over 2 is my cos, hyperbolic cos. So I want to write this term in terms of A hyperbolic cos kappa x plus B hyperbolic sine kappa x. Now why we want to do this? Okay, much easier to understand the solution when you apply the boundary condition. Now the first boundary condition is when x is 0, we can see that A cos 0 plus B hyperbolic sine 0 equals to 0. So what happened here? You can see that this the C must be equals to, the A must be equals to 0. Okay? Okay, because this is 1 and this is 0, right? That gives me A equals to 0. Okay, now looking at when A is 0, that will give me the equation with B hyperbolic sine kappa x. Okay, so now when x is L, I have B hyperbolic sine kappa L equals to 0 by the second boundary condition. Now we can see that with the second boundary condition that hyperbolic sine kappa L cannot be 0. Now why is that? Because the graph of hyperbolic sine, I'm not a good sketcher here, but it's like that, right? So you cannot find the solution when all the solution value here at 0, because you know it will goes up when x approach infinity. So there is no value of kappa L when it's equals to 0. Therefore, what we can say that it gives you also trivial solution. Okay, so I cannot consider case lambda greater than 0. Okay, now move on to my case 3, which is lambda less than 0. Now for this case 3, to let lambda less than 0, we consider kappa lambda equals to negative kappa squared. Okay, so it always be negative here for my kappa. Okay, so we have the second derivative equation, negative kappa squared. So I can see that the root must be complex root, right? So plus kappa squared x equals to 0. So my characteristic equation, if you forgot, I have to remind you, you have characteristic equation in the terms of m squared plus kappa squared equals to 0, m squared equals to negative kappa squared. Now, so what do I do here? So we can see that this is negative involving here. So m will be plus minus kappa I. So we have a complex root. So my equation now will be term involving cos and sine. A cos kappa x plus b sine kappa x. Okay, so now what we gotta do here, we gotta see the solution that we can obtain when you apply the boundary condition. So look at the boundary condition when x is 0. So we have cos 0 plus b sine 0 equals to 0. So this is 0, this is 1. So a equals to 0. Okay, that gives me the next solution. B sine, not hyperbolic sine, b sine kappa x equals, b sine kappa x. Okay, now we want to consider when x is equals to L. So the second boundary condition, XL will be b sine kappa L equals to 0. Now you can find all the values of kappa L when sine is 0, because sine is 0 at pi, 2 pi, 3 pi, right? But take note that b cannot be 0. If b is 0, then you don't have solution. So we gotta make sure for this third case, you make sure that b is not 0. So what we have here, sine kappa L equals to 0. Kappa L, the values when sine is 0 is you have pi, 2 pi, 3 pi, and so on. So kappa L equals to n pi. So what is kappa? Will be n pi over L. Therefore, we have obtained our solution, which is equals to Bn sine n pi over L for n equals to 1, 2, 3, 4, and so on. Okay, by right, we should write it in terms of summation here. Okay, I'm just going to write the summation part here, which is summation n equals to 1 to infinity Bn sine n pi over L. Okay, but remember that by choosing lambda equals to negative kappa squared gives us the non-trivial solution, or this called the eigenfunction. Okay, now we gotta recall back earlier on, we have also the function involving t, right? So let's looking into this equation now. Minus c squared, no, this will be like this. So the t equation earlier on is like this, right? C squared t equals to lambda. Now when lambda equals to negative kappa squared, so let's solve for this one. So similarly, we'll get similar approach like the x term. So we have, so you will have a complex root. Again, with the complex root, I can write this as Tn x equals to Cn cos Cn pi t over L plus dn sine Cn pi t over L. Okay, so I hope you agree with me. Okay, let me just tell you why the equation becomes like that. Okay, if you don't remember, so this will give me complex root, right? Because the characteristic equation gives m squared plus k squared c squared equals to 0, m squared equals to negative k squared c squared. So m will give me plus minus I, taking the square root, right? You have a negative 1, which is I, and then kc. Okay, now we have shown earlier on my k, or my kappa here. I mean, I have to say kappa, but I mean, it looks like k. We already obtained earlier as n pi over L. So that's why I'm writing it as C n pi over L. C n pi over L. And then this is involving t here, not x. Gosh, I am doing so many mistakes here in terms of writing. Okay, so just be careful when you're doing it. Don't do too rush like how I'm explaining to you. Okay, there you go. So we have obtained this general solution. uxt, such as uxt equals to big X and small t. Now we don't have to write the constant many times, so I'm just gonna write it for my c here. So I have earlier on for my x, sine n pi x over L, and then my t term here, cos Cn pi t over L plus dn sine Cn pi t over L. Okay, so this is what you got, the general solution. So now the next step, hopefully that will be the final step we want to do, is to solve for Cn and dn. So we can do that by looking into the initial condition. Okay, so we are given the initial condition. So now we can use the initial condition to solve for Cn and dn. So let's look at the first initial condition. So we have x0 equals to fx. So when t is 0, what do we have? So substitute t0 at that given xt equation. So we have summation n equals to 1 to infinity sine n pi x over L Cn cos 0 plus dn sine 0. Okay, sine 0 is 0, cos 0 is 1. And this is equals to f of x. Okay, so by right, because my t is 0, I should write this as 0. Okay, that gives me n equals to 1 to infinity sine n pi x over L Cn equals to fx. Okay, now if you look at this solution for my Cn here, So this is my half range series. Okay, my half range series where my Cn is given by 2 over L integrate from 0 to L fx sine n pi x over L dx. So I just need to write a comment here. So you have to search for my videos on half range series, okay, to see that why this is like that. Oops. Okay. So by the half range sine Fourier series. Okay, so I get my Cn value. Now you can, what you gotta do now, you want to find the solution for dn. The solution to dn you can obtain by using the second initial condition. It's given by taking the derivative, which is equals to gx. So partial u over partial t x0 equals to gx. So what I gotta do here, I got to differentiate my u xt solution. Okay, I have to differentiate. Let's differentiate this with respect to time. This is my u xt solution. Okay, so let me just, this will be a constant. Now differentiate cos will give me negative sign, and we have this one Cn pi over L in the front, and then Cn pi over L in the front. Differentiate sign will give me cos. Okay, so having that in mind, let's write it. Partial u over partial t x0, and don't forget when t is 0. So maybe I want to differentiate first instead of putting t0. Okay, so differentiate first, that give me summation n equals to 1 to infinity sine n pi x over L. Okay, I have negative Cn pi over L Cn cos. Okay, taking the, is it cos or sine? Earlier on I wrote it cos, right? So that will be negative sine. Okay, so I gotta erase this. Oops. Somehow my computer is running very slow. Okay, so bear with me. Sine C n pi t over L, and then we have plus C n pi over L dn. That will become my cos Cn pi t over L. Okay, so what I did, like I said, differentiate the u with respect to t. Okay, this is my u equation here. So this is my equation here. So now you take the derivative with respect to t. Okay, now what I want to do next is when t is 0. Okay, let's substitute when t is 0. Okay, so what I have, partial u over partial t when t is 0. I have x will remain constant. So we can see that when t is 0, sine 0 is 0, cos 0 is 1. That will give me Cn pi over L dn, which is equals to gx. Okay, so we know what is gx. Okay, so similarly, by the Fourier. Say, by the half range sine Fourier series, you know that dn is given by 2 over c n pi. Okay, 2 over c n pi. Integrate from 0 to L gx sine n pi x over L dx. Okay, so that's my solution. Okay, so we have looked into this solution for this vibration string on finite interval. So the solution is given by this equation here. Okay, this UT equation where my Cn and Dn are obtained by the first and second initial condition. So this is my equation for Cn. And then for my dn, this is the equation for my dn. Okay, so I don't want to keep this video too long. So if you want to look at this explanation to this, you can watch my next video. Okay, next video on wave equation. Okay, that's all for today. Bye.